Hi, everyone. In the previous video, we defined the Lebesgue outer measure for a subset of R, and we're able to calculate the Lebesgue outer measure of a few very simple sets. If you will recall, at the end of the last video, we returned to that wish list of properties that we would like for a measure to have. And in this video, we will see how the Lebesgue outer measure satisfies some of those properties exactly, while only satisfying a modified version of another. We will proceed through these one by one, stating the property that the Lebesgue outer measure satisfies, and then proving that it does indeed satisfy that property. So to begin, the first thing we want to show is that the outer measure of any interval is just the length of that interval. So we really just want to show that mu star of I is equal to L of I for any interval I. Now, what actually makes this a tiny bit complicated is that when we say interval here, we really mean any sort of interval. So we could be talking about, for example, an bounded open interval, a bounded closed interval, a bounded half open, half closed interval, or the other way around, half closed, half opened. But then we could also be talking about any unbounded interval. So we could also be talking about, say, a to infinity, or closed endpoint a to infinity, uh, minus infinity to b, open or closed. And indeed, we could also just be talking about all of R. So one of the things you can see, right, is that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different cases, right? I don't want to sort of deal with each of these one by one. That would actually be fairly tedious. So what I will actually do is start the proof by looking at the case of a closed and bounded interval. You may recall from Math 5610, closed and bounded intervals have some very nice properties. So we'll make use of those. We will then, once we have that, move to establishing that it works for all bounded intervals. And then we will also handle, as a separate case, all unbounded intervals. So essentially, we will prove this for closed and bounded intervals. We will then extend that to just bounded intervals, and then we'll extend further to all unbounded intervals as well. Now, there is one minor point I want to make before we move on. And that is that when we talk about the lengths of these intervals, or indeed when we talk about outer measure, we do want to allow the possibility that these things are infinite. So, for example, right, if I take the interval from a to infinity, right, that is an unbounded interval. Its length should be infinite. Now, you can get into some problems, and indeed, if we had a full semester course in measure theory, one of the first things we might do is actually discuss in depth the extended real numbers. Those are essentially the extended numbers with a notion of infinity added in. And then you need to talk about properties, arithmetic properties of how what is a plus infinity? What is infinity plus infinity? What's infinity minus infinity? Can you even compute those things? We are sort of avoiding that for the sake of getting through. But the length of this interval, right? The length of any interval is upper endpoint minus lower endpoint. So this should be infinity minus a, which is indeed just infinity. So we will be doing some very basic arithmetic at times with infinity, but generally this will work exactly the way that you think it should. So this is the plan. We're going to first start by proving this theorem for closed and bounded intervals. All right. So let's begin. And let's start with the case, let I be the closed and bounded interval AB. All right. So the first thing that we will note is that for any epsilon, this interval I, which is just AB, is contained in the open interval A minus epsilon over 2 to B plus epsilon over 2. All right, so I'm just taking this open interval, sorry, this closed interval. I'm building this open interval that this closed interval sits inside of, and notice that I'm demonstrating that I can sort of do this as closely as I would like. I can make these endpoints as close as I would like to AB, but they need to be a little bit outside, essentially. Okay. Now, if we do that, the outer measure of I, by definition, the outer measure of this interval is the infimum over all open covers of this, and it's the sum of the lengths of those intervals in the open cover. Now, in this case, note that this single interval is an open cover for this set. So this must be less than or equal to, so the infimum over the set of all open covers must be less than or equal to the infimum over this particular open cover, and the length of this interval is just B minus A plus epsilon over 2 minus negative epsilon over 2. It's just B minus A plus epsilon over 2. So that's the length of this particular open cover. Okay. And this holds for all epsilon greater than 0. And so if I have that the outer measure of I is less than or equal to B minus A plus epsilon over 2 for all epsilon greater than 0, I can take a limit as epsilon goes to 0, and I get that the outer measure of I must be less than or equal to B minus A. Now, keep in mind, right, my goal is to show that this is equal to B minus A, because this is actually the length of the interval I, right? So I'm sort of halfway there. What I'd like to do is show the inequality in the other direction. All right, so let's now do that. Okay. So the punchline of this piece, right, is this inequality. Now let me switch colors here because we want to prove the inequality in the opposite direction. So now let IN be an open cover of I, any open cover. Now, recall that I is a closed and bounded interval. Okay. By the Heine-Borel theorem, remember the Heine-Borel theorem says what? It says that closed and bounded subsets of Rn are compact. So by the Heine-Borel theorem, the interval I is compact. And hence, what does compact mean? Compact means every open cover has a finite subcover. So if I have this open cover of I has an open subcover. And we're just going to call that I sub k, with k going from 1 up to some capital N, right? But it's finite now. Okay. All right. Now, I'm going to have all these intervals in my subcover, this finite number. I want to order them in a particular way. Like I have a finite number of them, and I want to pick them so that like there's a particular one that's the first one and the second one and the third one. So what I'm going to do is I'm going to order order the IK such that so I want the left endpoint A to be in I1. I want the right endpoint B to be in IN. So basically, I want the left endpoint of the interval to be in whatever the first thing in your subcover is. I want the right endpoint B to be in whatever the last interval in your subcover is. And then I want to order the rest of them. Essentially, I want to order these. One way to think of this is I want to order them from left to right. So this sort of gives me the leftmost thing. This gives me the rightmost thing. And in between, I want to order them such that if I take two consecutive ones, they need to overlap. So their intersection is not the empty set for each k in 1 up to n minus 1, right? So I2 and I3 need to overlap, and I3 and I4 need to overlap, and so on and so on and so on. And these two conditions require that I'm working my way from left to right. Okay, so this is just how I want to order these. Now, doing that, okay, let's look then at the summed k equals 1 to capital N of the lengths of these intervals. Okay. Well, I can just write out, right, what these lengths are, right? So I1, let's say that I1, this is a little interval, and let's say its endpoints are A1 and B1, so its length would just be B1 minus A1. I2, let's say its endpoints are A2 and B2, B its length, so on and so on, right? All the way up to Bn minus An. Perfect. Well, let me rearrange these a little bit. Okay, this is a finite sum. I don't have to worry about the value changing potentially when I rearrange things. It's just a finite sum. So I'm going to first write B sub capital N. And then, so I've got a Bn. Now I'm going to pair things together. So I've got a minus An here, and then I'm going to have a B sub N minus 1. So I'm going to do B sub N minus 1 minus A sub N. Plus, I have a B sub N minus 2 minus A sub N minus 1. And I'm going to keep going, okay? I'll end up with a A2, with a B1 minus A2, and then a minus A1, okay? So this really is all the same things, just grouped together in a slightly different way. Now, the reason I want to reorder them in this way is if I do this, I have B sub N minus 1 minus AN. So what is this? This is the lower endpoint of IN and the upper endpoint of I sub N minus 1. Well, remember, those two must intersect, right? They have a non-trivial intersection. So that means that AN must be less than B sub N minus 1. So this quantity must be positive. Similarly here, each of these terms is non-zero because of this intersection property. Okay, so if we get rid of all those terms, all we'll do is make this larger. Make this smaller. So if I get rid of all of these, I make this smaller, and in fact, right, again, these are all non-zero, so that'll actually be strict. So I get B sub N minus A sub 1. But again, given that A was in the interval I1, that means A1 must have been less than A. And given that B is in I sub N, B sub N must be greater than B. And so this difference is greater than or equal to the difference B minus A. Okay. And so what do I have? I have that the sum of the lengths of these open covers must be greater than or equal to b minus a. Well, if I then take an infimum of all of these things, given that each of these is bounded below by b minus a, when I take an infimum, the infimum must also be bounded below by b minus a, and so hence the outer measure of I is greater than or equal to b minus a. And sorry, I should have said here, this inequality, it doesn't particularly matter. This is also strict. But remember, the important thing here is that even though you have a strict inequality here, you end up with possible equality here. Each of these is bounded below strictly by b minus a, but in the infimum, they could be approaching b minus a. So it could be, this has to be greater than or equal to, okay? Well, now I have that the outer measure of I is less than or equal to b minus a, and the outer measure of I is greater than or equal to b minus a. And so we conclude that the outer measure of I must be equal to b minus a, which is precisely the length of I. Right? That's how we define the length of the interval I. All right, so this is the proof when I is a closed and bounded interval. Okay, but what do we do when I is not closed, just bounded? Or what do we do if it's not bounded at all? Well, it turns out we can actually use this result to help us substantially with the rest of our proof. Let's erase here, take a moment to regroup, and then we'll very quickly knock out the rest of these cases. Now, in both of these, I just want to remind you again, we've already we've seen this before, but both of these we're going to use heavily the monotonicity property of the outer measure. Now, remember what the monotonicity property of outer measure says. It says if A is a subset of B, the outer measure of A must be less than or equal to the outer measure of B. We're going to make heavy use of that in completing this proof. Great. All right. So we've dealt with I as closed and bounded. Now let's just take I to be bounded. Okay. So let I be a bounded interval. All right, so we're knocking out those other cases, where it's the interval of the form A comma B, but whether it's open or closed at the endpoints, we don't really care, right? All right, so let I be a bounded interval, and let epsilon greater than 0 be given. Okay. Now, I want to choose a closed interval, okay? So let J be a closed interval such that I want J to be a subset of I. Okay. So I want J to be a closed interval that's inside this interval I. That means, by the way, J is also bounded because it's a subset of a bounded set. Okay. And I basically want J to be a good approximation of I. So what I want is I want the length of, I want to choose this in such a way that the length of I minus the length of J is less than epsilon. Now, you can actually write out explicitly how you would do this, right? So like if your interval was, let's say the interval you were dealing with was like A, B, the open interval, then you would choose the closed interval A plus epsilon over 2, B minus epsilon over 2. Okay, and so now you had this closed interval or this open interval AB, and you're just moving a little bit up here to a minus epsilon, or sorry, to a plus epsilon over 2, a little bit down here to b minus epsilon over 2, right? And you now have this closed interval that sits inside here, but it's pretty close, right? It's sort of within epsilon in a way of that open interval I. All right, this is actually a trick we're going to see several times in measure theory that you can sort of, where you sort of try to approximate a set of one kind by a set of a different kind, but you just make them sort of arbitrarily close to one another. All right, now if we do that, okay, so what happens? Well, let me rearrange this. So if I move the epsilon to this side and move the length of j to the other side, that inequality gives me that the length of I minus epsilon is less than the length of j. But now j is a closed and bounded interval. So, well, let's see, its length is just its outer measure. Right, we've already proven this for closed and bounded intervals. All right, but using monotonicity, j is a subset of I, so the outer measure of j must be less than or equal to the outer measure of I. Okay. But I itself is a subset of I closure, right? So I closure, right, if this is I, let's say this is my interval I, that's a bounded interval, right? I closure is just I union with all of its limit points. It just gives us the closed interval AB here. Okay. So I is a subset of I closure. So again, using the monotonicity, I get this. But I closure is a closed and bounded interval. So this is simply equal to the length of I closure. But the length of I closure is B minus A, just as the length of I is. And so we get this. So what do we have? So we have the length of I minus epsilon is less than or equal to the outer measure of I is less than or equal to the length of I. So taking a limit as epsilon goes to 0, gives me what? It gives me, this holds for every epsilon greater than 0. And so in the limit, I get that the length of I is less than or equal to the outer measure of I, which is less than or equal to the length of I. Marker's dying on me. So what does that give? So that just means the outer measure of I has to be equal to the length of I. Great. So now we've done this for any bounded interval. So we first did it for a closed and bounded interval. Now we've extended that to a generic bounded interval. Now the only thing left to do is to prove this for unbounded intervals. Okay. So now separate case, let I be any unbounded integral, or sorry, unbounded interval. Okay. Well, then for each natural number n, there exists a closed interval J. Oh, sorry, I guess I should say a closed and bounded interval J, which is a subset of I, with the outer measure of J being equal to n. Okay, so again, here the idea is you have some unbounded interval, like let's say it's, a to infinity. Well, if you take, say, the closed interval a plus 1 up to a plus 1 plus n, right? This has length n. It's a closed interval. It has length n. Because it's a closed and bounded interval, its length is equal to its outer measure. So it has the outer measure n. You can always do this, okay? If it's from minus infinity to b, you might have to think think again about how to define these, but you can always do this. All right. So we have n is the outer measure of j, which by monotonicity must be less than or equal to the outer measure of I. But I now have that the outer measure of I is greater than or equal to n for all natural numbers n. So this holds for all natural numbers n. And the only way that can happen is if the outer measure of I is infinite, which is the same as the length of an unbounded interval. Okay. And so now we get the result for unbounded intervals. Okay. And that completes the proof, right? So we start by proving it for closed intervals, closed and bounded intervals. A lot of the work actually happens there. And then we use essentially approximations by these closed intervals, right? So we take a bounded interval I, we approximate it from the inside by some closed interval, and then you use monotonicity to get the result. Similarly, for unbounded intervals, we start approximating it, but you see that we can approximate it essentially by any closed interval of arbitrary length or arbitrary outer measure. And so monotonicity here gives us unboundedness of the outer measure. All right. So this is nice. This gives us our first result. It's sort of ironic in a way. I think, when you look at the three proofs we're going to do in this video, this in some ways is the one that seems just the most natural and intuitive. And I think it's actually the one with the longest proof. So it's not always the case, right? And we've seen this before in analysis, but it's not always the case that the intuitive theorem has a simple or intuitive proof. Often, in fact, it can be quite the opposite. All right, the second theorem that we want to prove, right, going back to that wish list, is about translation invariance. Okay, so we're really proving that the outer measure is what we would call translation invariant. What that means is if I take any set E in R and take a real number x, then the outer measure of the set x plus E, the set x plus E is just take all the things in E and add x to them. So you can think of this geometrically as you have some set in R, you're just shifting it by x units, right? If x is positive, you're shifting it to the right. If x is negative, you're shifting it to the left. But the idea here is that the outer measure of x plus E, it ought to be exactly the same as the outer measure of E. You're just shifting, right, the set. You're not really changing the lengths of anything. So the outer measure should stay the same. That's what we'd like to prove. All right. The fundamental idea here is that if you have an open cover for E, then, and let's say that's IN, so the INs form an open cover of E, then X plus IN should form an open cover for X plus E. And vice versa. If you have an open cover, say K sub N for X plus E, then if you shift everything down by X, then negative X plus Kn ought to form an open cover of E. Okay, so the real reason this all ends up working out is that you can directly the sets of open covers you can form a bijection between them, and it's a very simple bijection, right? And that's really why this ends up working. Okay, but let's read out some of the details here. Okay, so let E be a subset of R and X be a particular value in R. And let's take an open cover. So let I sub n be an open cover of E. Um, then it's certainly the case that the outer measure of E must be less than or equal to the sums of the lengths of these particular intervals. This is a particular open cover. The outer measure of E is the infimum over all open covers of the sums of the lengths of the intervals in those open covers. So this has to be like any particular, this is an element of the set you're taking the infimum of. So this must be less than or equal to this. Okay. Now note that x plus in is an open cover of E. Oh, sorry, of x plus E. Okay. And so we have the outer measure of E, right, which we already know is less than or equal to the sum of the lengths of the INs. The length of a particular set is not, length is translation invariant. So we get this. And so if I think about the outer measure of x plus E, it is the infimum of all of these things. Okay. But for any particular open cover, this is less than or, sorry, this is greater than or equal to the outer measure of E. So the things that you're taking the infimums of are all bounded below by mu star of E. And so this must be greater than or equal to mu star of E. So again, for an arbitrary open cover of E, the outer measure of E is less than or equal to the sums of the lengths of the x plus INs. But the infimum over all open covers of these gives me the outer measure of x plus E. And so this must be less than or equal, or sorry, the outer measure of x plus E must be greater than or equal to the outer measure of E. Okay. On the other hand, okay, we can basically do this in reverse. If I start with mu star of x plus E, that would have to be less than or equal to the sums of the lengths of covers of the form x plus in, which is equal to sums of lengths of ins, because the lengths are translation invariant. But now I make a similar argument. The outer measure of E is an infimum over all of these things, but each of these things is bounded below by this. So the outer measure of E must be greater than or equal to the outer measure of x plus e. Well, now combining these two facts, I get that the outer measure of e is equal to the outer measure of x plus e, which is precisely what I wanted. Right? So again, intuitively, the real thing that's happening here is that there's a one-to-one correspondence between outer covers of E and outer covers, between open covers of E and open covers of X plus E, and the lengths, right, involved of all those intervals, those are translation invariant. So we actually get the same outer measure for these sets. All right, very good. Now, both of these were things, so the translation invariance and the outer measure of an interval being the length of the interval, those are both directly things off of our wish list, right? Now, the next thing we're going to prove is not something that's right off of our wish list, okay? The next thing on our wish list was actually countable additivity, okay? We are actually going to prove countable sub-additivity. Okay, so this is where we're not going to quite get what we wanted, but we'll get something sort of close, and then we'll actually revisit this a bit later once we define Lebesgue measure. So what I actually want to prove is if I have a countable sequence of subsets of R, say En, okay, then if I union all of those ENs together and then take their outer measure, I'll get a value which is less than or equal to taking the outer measure of each individual set and then adding them together. Okay. Now, again, this is less than or equal to, so you will sometimes get equality, but let's just focus on proving this result now with the inequality. All right. We're going to start by sort of getting rid of one quick case, okay, and then we'll move to the more difficult case. It actually gets rid of a bunch of cases, but then it allows us to make an assumption that will be helpful. Okay, so let's start the proof here by recognizing that if any one of our sets, so I have this collection of sets En, let En, so this is a subset of the power set of R, but it's countable. So each of these is a subset of R, but there's a countable collection of them. Okay. If any one of these sets has outer measure which is equal to infinity, so for any k, if mu star of ek is infinite, well, then our claim holds trivially, right? Because the right-hand side, which is the sum of the measures of the ENs, will be infinite, right? Because one of the values is infinity, the rest of them are non-negative, or well, they're non-negative. They could be zero, some of them, but I have infinity plus a bunch of other things which are all non-negative. That sum is going to be infinite, and hence the claim holds, right? Because then on the right-hand side, I have something is less than or equal to infinity. Well, that's always true. Okay. So if any one of my subsets of R has infinite outer measure, I'm done. All right. Now what do I need to deal with? Now I need to deal with a case where every one of them has finite measure. Okay. So now suppose mu star of En is finite for each n. That this is the other case, right? That they're all finite. Okay. And let epsilon greater than 0 be given. All right. Now, what I want to do is I need an open cover of each of the ENs. Okay. So for each EN, I will have like an open cover. I don't want to call it IN because N is indexing my sets, right? So I'm going to call the index of the things in the open cover for EN, I'm going to call them like the IJs. So let me explain this. So, or let me write this out a little more carefully. So for each natural number N, there exists a countable collection of open intervals and I'm going to call these I sub n comma j, where j, write this a little more clearly. So this is I sub nj, where j is a natural number. So for each n, basically for each of these sets, each of the ENs has a countable collection of open intervals. So I'm calling them INJ. This n is just signifying that this is the one going with EN. And then the j counts all the different open intervals that are in this collection. So that covers EN. Oh, sorry. And then I want to such that. Now, since I know that each of the ENs, right, each of the ENs has some outer measure, right, I should be able to choose this open cover so that the sums of the lengths of that open cover are as close as I would like to the outer measure of EN. So I'm going to choose these so that the sum of the lengths of the INJs, if I add them up over all j's, so from j equals 1 to infinity, I want this to be less than mu star of En plus epsilon over 2 to the n. Okay, so the idea is I ought to be able to get the sum of these lengths as close as I would like to this, right? So one way to look at this, I could rearrange this inequality. I'll put it back in a second, but I could rearrange this inequality to be the same as like this. Just saying choose your interval so that the difference between the sum of the lengths of these intervals and mu star of En is less than or equal to, or sorry, is strictly less than, well, strict inequality, epsilon over 2. Okay, now we just take that and rewrite it in this form. Now, so for each fixed n, I have this countable collection of things. Okay, but now what if I union those over all of the EN? So each particular EN has its own collection of open intervals that cover it. Now I take and I put them all into one big set. Okay, so then if I look at the set I sub nj, but now I don't just let j vary over n, I let n vary over the natural numbers as well. So what is this? This is a countable union of countable sets. There were countably many things for each n. There were countably many things in here. And then there are countably many sets En. The countable union of countable sets is countable. So this is a countable collection of sets. Okay. And it covers E. So this is a countable open cover of E. All right. Right. And why is this true? E is just the union, right, of all the ENs, right? So fix an N, the I sub NJs cover that particular EN, and then as you union them all together, right, over all N's, then this whole set covers the union of all the ENs, which is just E. Okay. Now, to finish this up, we just need to do a little bit of estimation here. If we can give ourselves, I don't even think we need to erase everything. Well, while we're at it, we might as well. Didn't have quite enough room on the bottom of the board to finish this. So if I now look at the outer measure of E, okay, right, that's really, E is the union of the ENs. Okay. This will be less than or equal to adding up the lengths of all of those little subintervals. So all those little open intervals. So from j equals 1 up to infinity and n equals 1 to infinity, the lengths of the I in j's. All right. Well, earlier, right, we said we chose the I in j's such that for each fixed n, this quantity was strictly less than mu star of En plus epsilon over 2 to the n. Okay, that's how we chose these sets I sub nj. Okay. But now, if I look at this, if I break up this sum, that would give me the sum n equals 1 to infinity of mu star of En plus the sum n equals 1 to infinity of epsilon over 2 to the n. Now, this is what I want, essentially. Okay. This piece, so the first piece I'm going to leave alone. This is a geometric series which simply sums to epsilon. Okay. And so what do I have? I have that mu star of the union of the ENs is strictly less than this quantity for every epsilon greater than 0. So taking epsilon to 0, we get the result that we want, which is that mu star of the union of the ENs is equal to the sum of the outer measures of the ENs. Sorry, not is equal to, it's less than or equal to. So we get precisely the countable subadditivity result that we wanted. Now, there's one detail that I sort of glossed over here that I'll go back and emphasize. You should worry a little bit. Really, what I did here in breaking up this sum, I have to worry a little bit about convergence here, because it's possible that this sum doesn't converge, right? And so I could sort of worry about, well, what happens if that sum doesn't converge? Well, again, if this piece doesn't converge, then even though none of the individual ones components of the sum was infinite, this whole thing ends up being infinity, and the result is trivially true. So we might as well assume that this sum converges. Since all of these are non-negative terms, that convergence is absolute. Similarly, this is a geometric series. It converges absolutely. So we have no problem actually breaking up this sum here, because in the case that this converges, it has to converge absolutely. This converges absolutely, and we're good. If this doesn't converge, then the result again holds trivially. So there is that small detail there that's worth noting, but it actually turns out not to be a problem here. Okay. Now, with that actually concludes everything we want to prove about Lebesgue outer measure. In the next video, what we want to do is define not the Lebesgue outer measure, but the Lebesgue measure itself. And what we will see is that Lebesgue measure is just Lebesgue outer measure restricted to a nice class of sets. So whereas Lebesgue outer measure is defined for any subset of R, we actually want to restrict ourselves to only sort of a subset of the power set of R. We'll see that by doing that, we actually recover some nicer properties than what we were able to get for Lebesgue outer measure. But we will begin that in the next video by first defining exactly what sets we want to consider to be measurable subsets of R.